I'm Professor Raissa D'Souza, and I'm an associate professor at the University of California in Davis, and I study computer science and mechanical engineering as my departments, but my background is very multidisciplinary. So I started out with a PhD in statistical physics, and then I did postdoc work in applied math at Bell Laboratories, and then I did postdoc work in theoretical computer science at Microsoft Research, where I still collaborate a lot too. So I have a very broad background in math and computer science, and now I'm learning a little more about engineering. The work that I do is more theoretical, so my research interests are a lot in modeling the mathematics of networks. So I'm very interested in understanding why networks form to have the structures they do, how does the function interact with the structure, what are the best kinds of structures for particular functions. And right now I'm still trying to make them more applied. So that, I think, is a real challenge. We can make many beautiful proofs about systems, but trying to understand how they connect to real engineered systems is still a very broad and open question. And networks, to me, is very exciting because we see them in engineered systems like sensor networks, the internet, the World Wide Web, but we also see them in biological systems like gene regulation networks, and also in social systems like economies. So it's very interesting to understand what makes all these networks similar and what makes them different. That's a big challenge, big question. And I think that ultimately it's very nice to understand aspects of self-organization. What does it mean? How can we control it? One of the particular systems that I've been studying, or particular aspects I study, is phase transition. So big changes in a system's properties in response to a small little change in an environment situation. Like if the classic example is spins aligning as you reduce temperature. So as you lower temperature, all of a sudden you get a magnetic moment and things become magnetized. So that's an example of a phase transition. And some of the work I've been studying is looking at how self-organized patterns influence the onset of phase transitions and how we might control where a phase transition happens or how abruptly it happens. So that's really a large goal, understanding self-organization, the interplay of self-organized structures, and when it elicits phase transitions and how we might control it. But to make progress, I think you really have to work on very specific models, especially from the scientific method. So, you start with toy models that help you gain insight into this bigger picture. So that long picture is really this idea of self-organization and phase transitions. But right now I study specific systems. So first, I really love doing science because I think it's a very creative endeavor. So it's always different every day. You really have to think outside of your normal perspective. Sometimes when you're stuck, you go take a hike in the mountains and you come back and you have a brand new idea that you never would have had. So it's a very creative process. So I really love that creativity and that every day I'm supposed to be learning and studying new things. So it really keeps you active mentally and feeling like a student. I've enjoyed it very much. It's been very stimulating and also productive. Oh, it's beautiful. So the research days have been very intense and focused, so much intellectual exchange. So not a lot of time for tourism in Klagenfurt. So I haven't yet been to the city, but one thing that I've loved very much so far is swimming in Wörthersee. Very beautiful. And Carinthia is very beautiful. A little bit, yeah,
Is
yeah.
anything special you like?
Well, I like Wiener Schnitzel and apple strudel, and we've had some very nice beers too. So it's been definitely a wonderful visit, and it's a fantastic place.